The second Gauss-Markov assumption is the assumption about normal distribution of residuals. And so frequently you'll hear this, that the residuals must be normally distributed. But why? Well, before we talk about why, first I want to show you exactly what we're talking about here. So here's a histogram of the residuals from a pretty simple linear model, the same linear model I showed you before that had heteroscedasticity. So as you can see here, the residuals, they're pretty wide. We have some really big residuals, and from a histogram it's tough to determine whether they are normally distributed, and that's the reason why we use these QQ norm plots. And so you'll see here's the QQ plot, and in order to have a pretty good understanding of that, I need a reference line. And there's my reference line, and you can see that it's not normally distributed, or at least there's some deviations in the tail. So what does this mean, and how does this come about? Well, so the first thing is it means very little in terms of the parameter estimates. So the B's and the A's, the normal distributions of the residuals have mostly to do with hypothesis testing. So why is that? Well, in order for us to really have a good grasp of it, I'm going to shift over to, I hope I can find it. Maybe I can't. Whoops. I have an applet that I'm running here. Yep, there we go. Okay, I have an applet here where I can demonstrate the central limit theorem just by taking samples. And the most important aspect of this is for us to appreciate that when we take a sample, and here's a sample of 5 at a time. Each time we take a sample, we get a sample with a mean. And that mean is going to have a distribution about it. So this is the sampling distribution, and this is the distribution of means and the distribution of standard deviations. Now this is a standard deviation of an n of 1, or excuse me, an n of 5. And every single time it keeps dropping us to a standard deviation where we had our first standard deviation. We have 3 repeated samples of 5. And right now what we aim to do is to be able to replicate a mean of 16 with an appropriate distribution around that mean so that we can approximate this population parameter. Now, what does all of this mean in terms of parameter estimation and hypothesis testing? Well, with the central limit theorem, we know that as the sample size increases, the sampling distribution of the mean approaches normality. So I didn't show you that, but what I did is I showed you little tiny samples. Now if I kept clicking on that and running through it a lot, eventually we'd have a sampling distribution of means that would be normal. And we get the same effect if we shift from mean, because mean is a parameter, it's a parameter of a single value. We get the same distribution of parameter estimates in regression. So as n increases, the sampling distribution of regression parameters also approaches normality. And it approaches normality regardless of the distribution of errors. So that's an important part. So as the sample size increases, the sampling distribution of regression parameters approach normality regardless of the distribution of errors. Well, why is normality so important? Well, remember, normality is important because so much of what we do in statistics, ordinary least squares, hypothesis testing, relies on the normal distribution. If we don't have a normal distribution, it's very difficult for us to make inferences and defensible inferences. So that normal distribution hangs over us all the time. Now, for small samples, the sampling distributions of our parameter estimates are not necessarily normal. As you could see in that little Java applet, you're not always going to get a normal distribution of these errors or of our parameter estimates. And you can see here, if I just keep clicking on this, at some point I might actually get something that looks very odd, maybe skewed. So you see here, look, I keep piling up a bunch of values here. The distribution of my means, think of this as a parameter estimate, doesn't look normal at all. Now maybe I'll get a few dots here, and notice that now I've got a skewed distribution. So that distribution doesn't look so good with small sample sizes. Okay? Now, for small sample sizes, like in the case here, our sampling distribution of our parameter estimates are not necessarily normal. They will be normal only if our errors are normally distributed. Okay? Now, our errors being normally distributed is this assumption that we were talking about. We need a normal distribution of errors to produce a normal distribution around our parameter estimates. Now, why is that important? Well, because we calculate standard error around our parameter estimates, and the standard error that we calculate around our parameter estimates assumes normality because it certainly assumes that there are two sides, right? Two sides to our parameter estimate, and that our parameter estimate could go in either direction. So what we have is we have a parameter estimate that's going to be in the center. So look at our Java applet here. Say we've got a parameter estimate here, and that there is an equal probability that the parameter estimate could be on either side of this, right? So that what we assume is that the errors are going to be distributed evenly, not uniformly, but evenly on both sides, so that our parameter estimate and our uncertainty around that parameter estimate is going to be consistent above and below it. And that's the reason why we do two-tailed tests, because it could go in either direction, and we assume that there is an equal probability and an equal distribution of errors on both sides. The failure to meet the normal distribution of residuals means that it doesn't affect our parameter estimate per se. It affects our inferences of that parameter estimate. So I know that this is a complicated one, and I hit you with a complicated assumption right away, but I want to make clear that the distribution of residuals for homoscedasticity is different than the normal distribution, because heteroscedastic residuals can also be normally distributed. As you can see in my distribution of my residuals here, well, not perfectly normal, but pretty close. You know, there's some deviations. But the most important thing is that when we're dealing with hypothesis testing, a violation of normality in our residuals leads to questionable hypothesis tests. Okay? And we'll talk about this in greater detail when we go to the applications and the interpretation of our regression. So Gauss-Markov 2 assumption, normally distributed residuals. The next assumption I'm going to cover in the following video is the independence assumption of residuals. So stay tuned for that.